Hey guys, I'm Alyssa,
And I'm Henry.
and we're back with ACM Cyber for another week of fun reverse engineering workshops. This week, we're going to be teaching you Buffer Overflow, and this is going to be a really valuable lesson, as I'm sure you guys have just started or are just starting the infamous Bomb Lab. And yes, you can probably find many other walkthroughs and cheat sheets on how to do the Bomb Lab, but today we're going to introduce to you all the basics and just how to do buffer overflow the cyber way. So let's start. What is buffer overflow? Maybe you guys have heard of this from CTF walkthroughs, your favorite YouTuber Live Overflow, or you just use Stack Overflow, so you're familiar with the term. Let's start with the first word, a buffer. So what is a buffer? A buffer is any sort of well-defined segment in memory where you're storing data. So this can be an array of ints. It could be an array of longs. It could be a string, which is really just an array of cars, right? And these have a specific start and end, right? You'll have array 0 up to array 15 for a 16-car array. And typically, if say you were trying to access array 16, you would get an out of bounds error. But due to certain insecure C functions like gets or stir copy, you can actually trespass these buffer boundaries. And anytime a program is trying to receive input and use these insecure functions, that's an opportunity to exploit the program. Specifically, anytime you feed a program an oversized input and all of that gets written to the buffer beyond the buffer, that's when you've committed a buffer overflow. Dun, dun, dun. So what does it actually look like inside the memory? Let's look at how a C program is laid out. So whenever you run your bomb lab executable or any C executable, it looks like this in memory. So in this diagram, we've got the code section at the bottom. It's the lowest address in your memory. All your functions live here, your main, your helper functions. And then on top of it, in another higher section of memory, you've got your data. These are your global variables, your static variables. Then on top of it is this sort of not super defined area of memory we call the stack and the heap. Now the heap goes up and the stack goes down. The difference is the heap stores all of your dynamically allocated memory, and the stack stores all of your function calls and your local variables. So anything that's not dynamic. This is memory that hasn't been fully defined yet, but all of this yellow section of memory is dedicated to either being put on the stack or the heap. And what we're going to care about today is how the stack works, because that's exactly where all of our buffers are going to live. So every time you call a function, all of the information about that function is going to be put onto the stack. What does that look like? Let's look at a stack frame right now. So every time you call a function, a new frame containing all the info to the function is put onto the bottom of the stack. As you may recall, the bottom of the stack is pointed out by RSP. So then we pop from RSP, as in we subtract from the stack pointer, but that actually grows the stack because it grows down into a lower address. And if you remember from our previous diagram, that makes the stack longer because the stack goes down. Yes, beautiful. It's like we're going from beef to BO, my favorite. So in the stack frame specifically, it's structured in a way where all the function parameters are put on top and then goes the return address where you want to go after the function has finished. So this will be an address that's inside the code section. And then there's a pointer to the previous stack frame, so the stack knows where to go back. It's essentially the previous location of RSP. And then after that are the juicy local variables, which we are trying to poke into. So what does it look like if I have the function that's in the walkthrough, vuln function. So here in the walkthrough, I defined a very vulnerable function. It's got two local variables, a useless integer, and a 16-byte car buffer. And then all it does is it calls gets to read from standard in and then write to the buffer. So if you look at the little table below it, we've got most of the stack frame minus the parameters since we don't have any parameters. And then what will be stored first is our return address, which is usually what's in RIP, the register RIP. We've got the previous stack pointer, which is usually RBP. And then we've got our local variables, useless and buffer. Let's take a closer look at buffer and how it'll work in the slides. Okay, so here we've got our program. To the left, we've got our input from standard in, a nice little hello world, which will be read into the program, be read by the program, and then the program is going to write it to that section of memory that was defined for buffer. Now, the reason why it looks weird, as in we're having buffer 0 at the bottom and buffer 15 at the top, is so that we can follow this convention of having higher addresses at the top and lower addresses at the bottom. So remember how I said the stack goes down, but here our buffer is going up? So if we are able to go past buffer 15 and then write to addresses above it, we'd essentially be able to disobey the growth of the stack and also write to what was previously on the stack. And that's our goal here with buffer overflow. What if I gave, okay, let's walk through the usual case first of me writing hello world to buffer. H would go into buffer 0, E would go into buffer 1, L would go to buffer 2, so on and so forth. So we got H, E, L, L, O, space, W, O, and then hello world is less than 16 characters, so the buffer would be fine. But what if I gave a really, really long sentence like, ACM Cyber is the best club on campus, and to standard in? The program, which uses gets, will actually still read all my characters and continue to write up past buffer 15. So first, that useless int would get overwritten. If that was the only extra piece of memory that I wrote into, the program would run as usual and everything would be fine. But if I happen to write higher into memory, say I happen to overwrite the base pointer or the return address, that's when things get spicy, because you'd be able to change not only variables that your program is storing and maybe reading, but you'd also be able to change the direction and the direction it's going and the functions that it's running. So now let's have Henry walk you through an example of this.
Whoa, okay. Whoa. All right, so like Alyssa talked about, essentially what this program does is you you have a vulnerable function over here, and then you have a char array, essentially a string in C++, but in C, a char array, and then you want to pass in you want to get a user input. So let's say, like in the previous example, how Alyssa passed in hello world, bus size right now is set to 32. So hello world will not overflow that, but let's say you enter a string that's 34 characters long. What's gonna happen is it will overflow outside of where like that memory is supposed to be stored, and it might overwrite something other such as the EBP or maybe the EIP, which determines where the address will actually return to, or like the address where the function will return to after it's finished calling. And so the purpose of this problem is essentially for you to exploit that. When you pass in, you want to enter a string specific enough that you want to jump to the success function up here. So then it will grab the flag from the flag.txt, and then it will print it out for you. So I'm just going to walk through it. I'm not going to solve everything, but if I do an object dump, all right, so if you look at the object dump, over here we have our main function, which is located at this address. I'm on a 64-bit system, so the addresses are a little bit long. And then somewhere you see a call Q for the Von function. So if you remember what Alyssa was talking about, when you call a function, essentially they also store it comes in like a frame where it has like local variable, it has a base pointer, it also has like an EIP where it stores where do you go after the function is finished executing. So essentially this address 88F will be stored inside this frame with the Von function when you call it. And over here you see this line. This line is really important because it's essentially saying so the line above you have RSP. You move RSP into RBP, which is essentially the base pointer, and then you subtract 20 in hex from RSP. So you subtract 20 in hex from RBP, meaning the hex will grow downward by 20 hex value, and 20 hex value in this case will be 32, and that corresponds to the buff size in the program earlier. So we know where the buffer is being stored, and this is the put function. Okay, so now that we know where the buffer is being stored, you can sort of guess where the EIP or the RIP is being stored as well. So if we go up a little bit, you see this is the location of the success function. So essentially what you want to do is you want to enter a string that has 32 characters, and that will take you outside of the buffer array. And then you want to insert a little bit more, another padding, so you can get out of the base pointer. And then you want to make sure you hit the EIP exactly, and then insert this address. So it overrides the EIP and have it jump to the success function right after the vulnerable function has been called. Oh, if you want to try this problem at home and you want to compile using GCC, you make sure you compile it with the stack breaker, or like the stack breaker turned off, because GCC by default protects against the stack buffer overflows. Oh, and inside the walkthrough, we have the different commands for GDB that you can use to help debug. I use objdump back then, but if you want another way, you can use GDB. So as Alyssa was talking about, you can type in info frame, and this will give you the different addresses and also where the local variables are stored. You can also use like print main to print out the address of main. I think the most useful part is this function over here, the x-64x. So this essentially prints out 16 bits or 16 words in hex value starting from from the base pointer, which in this case RSP. But what you can do is after you run your program, and then you can use x/16xw, but then instead of RSP, you switch it with RIP. So you can see what is the value currently being stored in secret, or what is being stored in the return register. Okay, so this is the other problem the other challenge we have. And this one is a little bit easier. So this one, essentially, you have to cause a segfault handler, or yeah, you have to cause the segfault signal to be triggered. And this function essentially triggers whenever there's a buffer overflow detected. And yeah, more helpful commands. I think that's it.
All right, so that was our introduction to buffer overflow. And just some quick pointers besides those GDB keywords and object dump are basically just whenever you're reading some source code and you see these insecure functions like stir copy or gets, that's when you know that your program isn't using bounds checking and is vulnerable to buffer overflow. these are actually insecure and like well known to be deprecated functions. There's already better alternatives like strt and copy or fgets that are much more secure and only read a specified number of bytes to a buffer. However, you'd be surprised by how many old and deprecated programs there are out there. So have fun with our challenges. They're live on acmcyber.com. And we'll be around for office hours Monday from 7 to 9. Have fun, you guys.